PE. All of this is negative. It's all below, isn't it? I'm losing PE. What this corresponds to is the steepest slope. That's not the minimum PE, guys. Look, let's just make up some numbers. -8, -9, -10. Now what's that number? -9, -8. You get it? I'm losing, but I'm just not losing as much as I was here. So this graph still has to go down more, doesn't it? But what's going to happen when I get to here? At that point, it levels off because now I'm -6, -2. You see what I'm doing? I didn't lose that much now. I'm now at the minimum potential energy. What's going to happen now? I'm going to start gaining energy. And yeah, I come up the hill. This is the bonding graph that you guys see in chemistry sometimes. How many people have ever seen a graph that looks something like this? It comes from the force graph, and I'm telling you, if you take college chemistry, college physics, you're going to run into this again. This is just the beginning, okay? Especially if you take quantum mechanics stuff and bonding courses. Okay, anyway, so where does the minimum PE occur? Does that make sense? If you pull something apart, watch me, hello. If you pull something apart and it's like got a bond and I let it go, does it have the potential to do something? Come back. And what if I push it together? It's got the potential to go out. That's exactly what we see here. When you're at the equilibrium bond length and you move outward, you just gained PE. And when you get too close, you gain PE. You with me? Does physics help explain some of this stuff for bonding then? Yeah, so that's what we're doing. Macro, micro, macro, micro. This is a microscopic kind of view of what's going on. Now, ready? This is called what distance? Equilibrium bond length. What would you call that distance? From here to here. It is the delta PE. In chemistry, that's your bond energy. How much energy would you have to add to get to 0 PE? That much. Where would the atoms be when they were at 0 PE? They might be here, but only for a moment because they're going to come shooting back out and go where? They're going to shoot right past that equilibrium. Where are they going to go? What's going to happen if they get really far out and that force gets really weak? You're going to break the bond, exactly. So when you get way out here, you've broken the bond. Does that make sense? So this is how much energy you have to add to break the bond. Say metal, a bunch of metal atoms all in a row. If I go to pull on this thing, what am I stretching? Yeah, the bonds, right? And so what's going to happen over here is we're going to be moving this way on the x-axis, which means this force is going to get bigger and bigger. Can you picture that? We did that in the lab. You put more stuff on here, it's going to weigh more, it's going to stretch more. Everybody with me? But eventually what happened to the, whatever we're stretching? It can break, right? Where on this graph would you be when the stuff rips apart and won't come back together? All the way out here? Hey, that looks like less force.
No, at the, like past the tip, like the highest point.
Like here? Yes. You keep adding weights and the stuff stretches and stretches. You add one more little thing and you're down here. Uh-oh. The attractive forces can't pull back. They've gotten weaker. What will the thing do? It's going to snap. Does everybody see that? Do you think that's cool? The bonding graph can help explain what's going on in our lab. What was our graph, though, that we made? What was the graph that we made?
Stress over strain.
Stress over strain. Doesn't the stress relate to the force? Doesn't the strain relate to the stretch? In our graph, I thought it looked like that, didn't it?
It's a curve.
Do you see this over here?
Yeah.
Where is it?
The tangent line.
Well, yeah, it is like a tangent line. It's right here, though.
It's right there, right?
It's right here. What is the slope of this line called? Young's modulus. And we said it was linear, right? But this is a curve, isn't it? But can a curve look like a straight line if you only look at a small segment? What's going to happen over here? It starts to curve, right? If you take a look at the engineering sheet that I gave you yesterday, there's a tensile strength. Do you remember?
Yeah.
We didn't put that last dot on the graph, did we? That last dot is going to appear over here. What does that tell you about this graph?
Not linear.
It's got a curve. Does anybody see how this graph now is this graph right here? Just flipped upside down. Do you think it's kind of cool that we're looking at a macroscopic behavior and saying, oh my gosh, it lines up with the microscopic bond diagram? I hope you get as excited as I do about this because I think this is kind of neat. You're smiling. You're wearing a varsity physics shirt. You're with me?
Yep.
Okay, good. All right, now, only one problem with all of this before I do more cool demos. We did a graph of stress versus strain for the rubber band, didn't we? This was all for like a wire. The rubber band looked nice like this, but then which way did it start to curve? It did. It started to curve up.
Oh, was that because I couldn't pull back anymore?
That's because it was like zigzag, wasn't it?
Did I tell you that already?
Yeah.
Then I'll give you the summary on this. The molecules, and remember, I'll say it again, it's only a model, okay? In real life, the strain, eventually when it breaks, it's going to have to level off.
Bless you.
What do you think about that? Comments, questions? You okay with that? Totally whacked out stuff, isn't it? Okay, look, I hope you really enjoyed that, but now it's time to talk about some more stuff.